Hello everyone. This is the homework video for special relativity part 1. I should turn the color for this to be okay. Okay, so the first multiple choice. Okay. Says which of the following scenario is an example of an inertial frame of reference? So inertial frame of reference is by definition where the frame of reference does not experience any acceleration. Okay, D will be the right answer in terms of a meteorite falling at terminal velocity. That literally means that the net force on the meteorite is 0. Question 2. In a thought experiment, a jet is traveling at 0.5 times the speed of light relative to the ground. There's another train that is traveling at 0.1 times the speed of light relative to the ground. The driver of the train flashes its light at regular time intervals to alert the pilot of the jet. Which quantity would the train observer and pilot measure to be the same? The speed of light is measured to be the same because that's the second postulate. Therefore, it is C. Third question. A spaceship travels to a distant star that is located 0.75 times speed of light. When it arrives, 10 years have passed on Earth. How many years have passed on the spaceship? So 10 years is the dilated time. Okay, because Earth measures dilated time. And on the spaceship, we measure proper time. So you just calculate the proper time. Okay. Which will be T is equals to proper time times by gamma. Using this speed, you can calculate for gamma. After you got gamma, rearrange for proper time. Okay, correct answer is C. Question 4. A spaceship travels at a constant velocity 0.8 times speed of light from Earth to Pluto. A scientist on Earth measures the length of the spaceship during its journey to be L and the distance between Earth and Pluto to be D. Which of the following rows of the table correctly identifies the measurement made by an astronaut on the spaceship? So the length of the spaceship would be observed to be longer. This is because that on the spaceship, the length of the spaceship is measured as proper, so it's longer than L. In terms of distance between Earth and Pluto, this is going to be a contracted length as measured by the spaceship, so it's smaller than D. The spaceship itself is stationary with itself, so it's measuring proper. And the distance of the journey is proper in terms of Earth's perspective. So spaceship would measure the contracted length. Question 5. Proxima Centauri is a star that is 4.2 light years away from our solar system. A spaceship travels to Proxima Centauri at 0.99 speed of light. What distance is traveled by as measured by an astronaut on the spaceship? You just need to length contract 4.2 light years. Okay, so L is equals to proper length. Okay, divided by gamma. Okay. Easy. Question 6. In a thought experiment, a train is traveling at constant velocity 0.7 c. At the front and rear end of the carriage, there are two automatic doors which open when their sensors detect a radio pulse. A radio pulse is fired from the middle of the carriage towards the front and rear as shown. Which statement correctly describes the observation made by a stationary person outside the train? This is the principle of simultaneity. Okay. To the perspective of the person outside the train, the rear door will open first and then followed by the front door. Okay, so it would be C. This is because that the train itself is traveling, but they both measure speed of light to be c. So as the store goes this way, light travels a shorter distance. However, light has to travel a longer distance for the store to propagate. A train traveling at constant speed v passes a platform at a station without stopping. A passenger on the train measures the time taken for the entire length of the train to pass the platform to be t, and the person on the platform measures the time taken to be tp. Um, okay, so let's say that determine this first question pretty much relies on a determination of who measures proper time, right? Which one is proper? So if you have a platform like this, let's just say this point is the platform, okay? Just this point is the platform, and then we have a train that's doing this, right? So, and then we need to define two events. The events has to be how this train is like traveling, right? So we can define event A as the front of the train meets with this point, event B as the end of this train meets this point, and it's obvious that proper time is measured when those two events are observed at the same location. Okay, this would also always be or obviously be the person outside the train, as in A and B both happened at this point, but the train itself measures a dilated time. Okay, so TT is dilated, TP is proper. TP is equal to gamma times TT. Therefore, TP over TT is equal to gamma. Sorry, which should be something like this. We know how Lorentz factor looks like this function, okay? So the correct answer is A. Coming up to question 8. Two observers are moving in two different spacecrafts at a constant velocity. At some instant, the observer in the craft A bounces a ball to the ground and then catches it again. Which of the following observer listed will measure the proper time? So the two events are happening at the same sort of location is in the spacecraft. Okay, and in a different spacecraft, these two events are in a different location, so not proper. Question 9. A person is sitting inside a windowless train. A ball bearing hangs from a string and attached to the ceiling of the train as shown. Based on this observation alone, what can be concluded by the passenger on the train? Um, because we see how the pendulum themselves are not deflected, which means that the system is inertial. There is no measurable acceleration. So C will be the right answer. Question 10. The diagram shows a stationary unidentified flying object, UFO. When it's traveling at 0.75 C, it will lens contract, so it will look something like C. Okay? Continue. Question 11. Outline two postulates of special relativity. This is just defining two postulates. Postulate 1 says that all inertial frame of references are equivalent. Physical laws are equally as valid in all of them. Postulate 2 says the speed of light is invariant across all inertial frames. Yeah, everyone, no matter how fast you're traveling against each other, you measure speed of light to be consistent. Question B. How does Michelson-Morley experiment supports the postulates in part A? In your answer, include the observation made in the experiment. So, Michelson-Morley experiment was this experiment that proved ether doesn't exist. Michelson-Morley experiment utilized interferometer and showed that ether doesn't exist. This is a challenged. This has challenged Galilean relativity, where we sort of require a frame that is truly at rest to describe physical laws. Postulate 1 is then formulated as the ether was defined to be the stationary frame, and Mitchell-Morley showed that it doesn't exist, right? So since Mitchell-Morley experiment conclude null results of ether, indicating that the stationary frame cannot be defined, which means that we don't have this spirit frame to define every the laws of physics to be valid in. That means we don't have to define, right? Which means every other frame is equally as valid. So postulate 2 is a direct consequence of Maxwell's theory, also the first postulate. In situations where the same beam of light is observed by two different observers, they're allowed to derive for the speed of light using Maxwell's equation. And since everyone has the right to use Maxwell's equation without any modification, because postulate 1, right? They should just look at that beam of light and conclude speed of light to be equal to this equation. But this expression is independent to the motion of observer, which means every observer measures speed of light to be the same value. Okay? Right, let's move on. Question 12. What is the difference between an inertial frame of reference and a non-inertial frame of reference? Inertial frame has zero net force. Non-inertial frame has non-zero net force and thus accelerating. Okay, it's pretty trivial. Question B. Outlines and experiments that can be performed to distinguish between an inertial frame of reference and non-inertial frame reference include the observation that is expected for each reference frames. So inertial frame by definition has zero net force, which means that there is zero acceleration to be felt. We just need to create a sensor that detects any noticeable acceleration, right? Just as we did in examples, we have a pendulum, right? This pendulum sort of get implemented to an angle, right? Carries an angle when the frame is accelerating. For any inertial frame, you won't see this pendulum to be deflected. Okay. Moving on to next question, question 13. Outline a thought experiment that demonstrates the principle of simultaneity of special relativity. So I used the lightning experiment, similarly to the example we did in class. So this thought experiment involves two inertial frames of references. First one, Jack's reference frame, and then Alex's reference frame, S and S prime, moving relative to S at speed v in x direction. So this is like you have to define your frame of reference first, and then we're gonna define our events. Two events. The first event is when the light bolt hits the front of the train, and the second event is the light bulb hits the end of the train. And then we analyze the situation, right, with something like this. So Jack would observe the lightning to be simultaneous because it's literally traveling at the same distance. So it's literally traveling the same distance towards Jack. Therefore, he would observe a simultaneous event. The reason for this is he sees both lightning bolts traveling at the speed of light c. And there is also equidistance. So using first postulate and the second postulate, he was able to conclude that event A and B are simultaneous. Alex, on the other hand, would see event A happens first, while event B happens later. This is because how Alex also sees speed of light to be invariant. This is second postulate, and he uses kinematics equation because he's sort of moving towards this beam of light, so it travels a shorter distance, right? And then while B has to move towards it, move to sort of have to chase the motion of the Alex, so end up with a longer distance. Okay, so and then question B says, why are thought experiments useful? Provide two reasons. So thought experiments are useful because they provide logical derivation when the experimentation is impractical, or you can still derive from abstract postulates. The second reason is because thought experiment provide logical construct straight from like theories or postulate. Okay, it could be a very abstract postulate, and it can be only phrased with words instead of mathematics. You can still use those logic in terms of deriving for a theory, right? It's very different compared to if you start with a math equation and then derive for its consequence. In this case, you start with like a general statement or general logic and then derive for consequences. Question 14. A spaceship traveled at constant velocity to a distant star. Upon arrival at that star, an astronaut on the spaceship measured the duration of its journey to be exactly half of what is measured by a person on Earth. Calculate the speed of the spaceship. Okay, so events are, just you have to identify the events, right? So departure and arrival will be the two events. And who measures the two events at sort of the same location? It will be the person in the spaceship, okay? And you were looking for the speed, so you want to define the velocity in terms of the Lorentz factor, and you sort of just rearrange, okay? I made it more convenient by defining a parameter called beta and derive for beta. Beta is like how much of speed of flight in percentage, right? So you end up getting 3/4 times the speed of light. Okay. Question B. Outline a feasible thought experiment that demonstrates time dilation. If you consider a moving train moving relative to an observer at v, this is the same exact thought experiment that it is used in the lesson booklet. Okay. So you consider a moving train moving relative to an observer at v. A beam of light departs from the ceiling of the train and lands on the floor. By the postulates of special relativity, the person on the train sees light travel a vertical path to the floor. Okay. It would then use kinematics equation to compute for the duration. The person outside the train would see light travels along a diagonal, which is a longer distance than the vertical distance, according to Pythagoras theorem. And he also sees the speed of light to be invariant. This is second postulate. And if he uses kinematics equation, he would calculate the duration using distance over speed and end up with a larger time, hence evaluating for time dilation. You do not need to prove for the equation, right? That would be too much for this question, but sort of logically demonstrate how time is being dilated. Next question, question 15. Here, a spaceship travels at constant speed, 0.2 times the speed of light to a distant star. Upon arrival, 18.7 years has passed on a person, passed for a person on Earth. What is the distance between Earth and the distant star as measured by an astronaut on the spaceship? Support your answer with calculations. Okay, so for these kind of calculation question, calculate for the Lorentz factor first, store it in your calculator, and then prepare it for later calculations. Okay, we know how spaceship measures proper time t0 because those two events, departure and arrival, are being observed to be stationary to the spacecraft perspective. But the distance between the star and Earth is then observed as proper length on Earth. Okay, so spacecraft actually measures proper time, but a contracted length. But Earth measures a proper length with a dilated time. Okay, this is also goes back to how we said that proper length and proper time are not measured by the same observer; they're measured by different observers. So Lorentz factor is equals to dilated time divided by proper time, or proper length divided by contracted length, and that implies your length is equals to proper length over gamma. It's by definition. Proper length is the speed multiplies by a dilated time. Okay, because proper length is measured as Earth's frame of reference, which involves a proper dilated time, and you get this expression. You can then rearrange for. Sorry, you can then substitute values for the L. Yeah, you end up with 3.66 light years. If you're not happy with light years, you can still use meters if you want. Just recall that a light year is the distance that light travels in a year. Um, this is how many seconds in a year. That's how many years that has traveled. This is how many like how many meters per second. So this multiplies that is literally the distance per light year in terms of um, yeah, this is the distance in meters per year. Okay. So to transform this into light year, you just divide with that, right? Which means you just need to calculate this and then put your unit as light years. Question B. As the spaceship approaches the star, it slows down to a speed of 1,000 meters per second to prepare for landing. How does this affect the application of special relativity to this scenario? Because it's slowing down, there's deceleration, causing the frame to be non-inertial. The spaceship's frame of reference stopped being inertial, as special relativity only works for inertial frames. This would no longer be valid during deceleration. After this deceleration, it is still applicable, okay, but the initial and final speed is quite slow. So Galilean relativity is just as fine. You don't need to transform it with like Lorentz transformation. Okay, 1,000 meters per second is like non-relativistic. Okay, Lorentz introduced the concept of relative frame of references. Lorentz transformation predated the work of Einstein but gave equivalent answers. In classical theory, space and time is observed as a absolute concept, while in special relativity, they're in a relative concept. What does it mean by the term absolute and relative space-time? So, absolute space-time would refer to a relativity where space and time are intrinsic for all observers. It's kind of like saying everyone should see space and time with the same perception. Okay, there shouldn't be any differences between space and time. They're expected to share the same perception of space and time, independent to the motion observers. There exists a stationary frame so that everybody sort of measures phenomena relative to this frame. In terms of relative space-time, in contrast, right, to a view where it is a view where space and time are relative, the perception of space and time depends on the observer's motion, and space and time are mixable among different frame of references. The mathematics that calculates the different perception in space and time is the Lorentz transformation, which is actually the mathematical framework for special relativity. Einstein just gave that mathematical framework a meaning. Okay. Yeah, so this question pretty much you just have to define what does it mean to be absolute and relative space-time, and pretty much that's it. Yeah. Question 17. The average lifetime of a person is 17 years. 70 years. Does this mean it is impossible for an average person to travel to a distance greater than 70 light years from Earth? Explain your answer quantitatively. Well, this depends on perspectives, right? 70 years of life is measured to be proper for the person himself. So to himself, 70 years is the time he has. And even if he travels at the speed of light, 70 light years will be the most distance he can travel. So it's true if you're measuring proper time. However, for every other frame of references, time must be dilated, and this therefore would take some time that's longer than 70 years, and hence be able to travel longer than 70 years, light years of distance. Okay, we do a calculation with a specific case. Say it's 0.99 c, and then the time is dilated to 400, almost 500 years, and therefore the observer can then travel. You can see the thing travel for at least 496 light years of distance. Okay. Um, okay. So also note that this is also consistent with lens contraction, as 496 light year is contracted to be less than 70 light years in the person's own view. Okay, they're all consistent with each other. A spacecraft is flying past the moon at 0.975 C. The craft is 125 meters long, according to a person on the spacecraft. At some instant, the craft is directly above a blinking light on the moon surface. The light takes 1.50 seconds to turn on and off, according to the person on the moon. Question A. How long does the light take to turn on and off, according to the person on the craft? Well, the proper time is then um, measured in the moon's frame, right? If you think about the blinking events of light, is happening at the same location on the moon. So the person on the craft would then measure dilated time. Simple calculation, very trivial. Question B. What is the length of the craft according to the person on the moon? Simple calculation again. Um, Hopefully there's no question on this. If there's any question, let me know. I can provide some help on it. Question 19. A small experimental craft is 2.5 meters long, according to a pilot on the craft. The craft can travel at speed 0.85 c. What is the length of the craft as measured by an external observer? So the external observer sees the actual contracted length, right? So you just contract the length. Question B, the pilot measures the time it takes to travel between 2 points in 60 seconds. How far does it take the spacecraft to travel in this time, according to the pilot and the observer on the ground? So in terms of the pilot, he sees the distance to be 1.53 times 10 to the power of 10 meters. This is, you just use the kinematics equation. However, for the observer on the ground, um, uh, this distance would be sort of this distance will be the proper length, right? Which is the proper length version for this. I didn't calculate for this, so I'm just going to do it now. Um, so the ground observer measures proper length. So it's just L0 is equals to L multiplied by gamma. What was my gamma? Is 1.898. So L is 1.53 10 to the power of 10. Okay, whatever this value computes, give me a sec. This computes to 2.90 times 10 to the power of 10 meters. Question 20. A cube has a side length of 1 centimeter and is initially at rest. With one edge in the x direction, it then travels at relativistic speed v in the x direction. The mass is 1.0 kilograms. Calculate the volume of the cube initially. So volume is just side length squared. Side length cubed. 10 times 10 to the power 10 to the negative 6 meters cubed. That's the volume. B. Calculate the volume according to an external observer when it is moving at speed v. We know that only one direction is length contracted, that is the direction along the direction of motion. So only one side is contracted, while the other two sides remain as 1 centimeter. Okay, so you just sort of, one side has been contracted, divided by 1 gamma, and then you just do the calculation. It's very simple. We are not being given a value for v, so it's expressed in terms of v is good enough. Question 21. In a science fiction, arc ship, our spacecrafts that will leave the Earth in order to colonize the far distant region of space. The people in the Ark ship will either be in stasis, it's like a long-term deep sleep, or many generations will live on the ship. So consider an arc ship that can travel at zero point 0.9 c that is being sent to a distant system at 2,500 light years away. So 1 light year, note that is the distance that light travels in 1 year. Calculate 1 light year in meters. Okay, once again, that should be quite trivial. Question B, calculate the distance that arc ship must travel according to the person on the ship. Is a contracted length, so you just divide by Lorentz factor. Question 21, how long in years does the journey take according to a person on Earth and a person on the craft? To a person on Earth, this is dilated time in which we get that, but to a person on a spaceship, you get a proper time. So this is that. So the events of this is still departure and arrival. Question D, as the ship passes the sun, it will not appear to be spherical. Calculate the ratio of the major and minor axes of the sun, and note that the sun will be, if the sun was spherical, then the ratio is 1. So this is when the sun is relatively stationary. If you observe it, while traveling at relativistic speed, it will go something like this, right? So this direction will be contracted to be a shorter axis, it's the minor axis, and this will be a longer axis. The lens contraction occurs along direction of motion. Original radius of the sun is r. This is the semi-major axis. In terms of the semi-minor axis, it's just Lorentz contracted. Okay, so you just do the calculation. Just do the ratio, right? And then make a substitution, cancel out the r. It's pretty much just Lorentz factor. Okay. All right. Following question, twin paradox. Okay. A twin on her 21st birthday, and an astronaut takes off in a rocket ship at speed 12 over 13 times the speed of light. After 5 years has elapsed on her watch, she turns around and heads back with the same speed to rejoin with her twin brother, who stayed at home. How old is each twin at their reunion? Okay, so as we sort of discussed this in class, if I haven't discussed this and if you're curious, you can let me know. Uh, the twin in the spacecraft has accelerated and changed frame of reference. Although time dilation is in both ways, okay, she would observe significant time passes on Earth when she is decelerating. Okay, so it turns out that the person going in the spaceship, although she also sees that the time on Earth is dilated, but because he has reversed his direction, there is like an acceleration going on, and it's a change of frame of reference. It's sort of while it's doing the deceleration or like turning around maneuver, you would observe like a lot of time has passed during that maneuver. So on the spaceship, the round-way trip takes 10 years. So she is 31 years old. But on Earth, 10 years of time is then dilated. So it's 26 years old. All right. Um, okay. Okay, so well, this one is, hold on, 5 years. Right. It will be 26 plus 21, okay? So the twin on Earth, the question did ask us to calculate their age instead of like how much time has elapsed. On Earth is 26 plus 21, which gives you 47 years old, while the person inside the spacecraft is actually younger at 31. Good. Right. Next question, causality. It's a very hard question. Questions like if you understand what does it mean to be causal or what does causality mean in general. It's a very hard question that takes some real thinking, okay? If event A is to cause event B, A as an event to cause B has to occur first, right? That makes sense. You have to, if you want to cause something, it better happens before something. And the question asks, is it possible in some reference frame that A appears to be the cause of B and in others B appears to be cause of A? It's like simultaneity, right? It's like we see two events simultaneous, but in different frames they're not simultaneous. Can we reverse the order if A causes B, but in a different frame it happens as B causes A? Obviously you can't, like it doesn't make sense. This is where we say how because special relativity accepts that you could have this relative asymmetry problem. It's fine, we don't need to solve it as long as it doesn't violate causality. Okay, we cannot accept that the relative asymmetry works for electric and magnetic fields because they're sort of unified, but the deeper meaning is that you can't violate causality. This cannot be possible. Two causally related events remain causal for every other observer. We can prove this with special relativity with the fact that the speed of light is not achievable. For A to cause B, some sort of signal or influence must travel from A to B. Since no information can travel faster than the speed of light, A and B must be separated by a something called a time-like or a space-like interval, which means that the distance traveled by light has to be greater or equals to the distance traveled between the two events. If this happens, then this event can be causal. A non-causal event will have the spatial separation between the two events being larger than what light can travel, which means if those two events happen at such a distance, then cannot be these two events cannot be causal. So then special relativity says you can reverse this order in different frame of reference. You can actually do that, but not for the cases where it's this. Okay, right. This is good. Right, that's it for this homework video. We'll see you next time.